welcome to another one of our crazy videos. This is the first one is going to talk about a more specific thing. I'm going to teach you how to read a mass spectrum. A mass spectrum, as the name says itself, is connected to the mass number. And I encourage you that if you do not understand, you can ask me questions in the forum or you can ask me questions over Zoom. Email me, but you could also just go back to the lesson about isotopes and the nucleus and just review what you know before and figure things out. It's always better to figure things out yourself. So this is a mass spectrum, and a mass spectrum can be written in many different ways. I just wanted to show you here. This is the way they write it in AP. So you see you have 5 peaks here on this spectrum, and each peak represents the mass number and the percentage of that isotope in nature, which means this is some kind of element that has 5 isotopes. The first isotope has a mass number of 90, and it's present in about 52% in nature, right? Let's say this is 52. The second isotope has the mass of 91 and is present in about 12% in nature. 12% of the element is this isotope. The third isotope has the mass of 92 and is present in the abundance of around, what is this? Say 13%. And so on. So that's what the mass spectrum does. Basically, it's a machine in which you put an element and it spits out a spectrum looking like this. The look can vary. I'll show you some different versions. For example, on this axis, sometimes it will say AMU, sometimes it will just say atomic mass, sometimes it will say gram per mole, sometimes it will say M through Z. Doesn't matter. This axis is the atomic mass of that element. That's what you need to remember. And this axis is usually abundance, or the relative size of the peak shows you how much more of one you have compared to the other. So let's check out some of the simpler peaks first. Let's look at this one. This one is very simple. It says label the element which can give a mass spectrum. It looks like the following. So you see this element has a mass number of 23, and you can see again here is M through Z. Ignore that. So mass number is 23, and relative abundance is 100. So it's just one isotope. This element has only one isotope. So let's look at the periodic table and try to figure out which element that is. You will notice that in the periodic table, the elements, as you go from left to right and then down, both the mass and the atomic number increase. So see, 3 and 7, and then here's 4 and 9, so both increase, 5 and 10, and so on. So if you keep going, you need to get to something which has the mass number of 23. So actually, there is only one element which is close to 23, and that's sodium, 22.989. But that's not 23. Don't get confused by this. In AP, you'll have a lot of questions like this. What does this mean? This just means that there is another peak here, but it's so small that it's not even visible. So in this case, you will search for an element which is very close to 23, or exactly 23. Because again, here it looks like it's one isotope, but you know that cannot be correct. Because it must be sodium here. It cannot be magnesium, because it's impossible that the average of isotopes is 24. And it's impossible that it's 20. It must be 23, because 99.999% of this element is 23, and there is probably a small peak somewhere under, like here, I don't know, it's 0.01%. It's not even seen in the spectrum. That's what we call trace elements. So basically you can ignore them. So let's check this one out. Let's see if we have sodium. Yeah, so it's sodium. Let's check this one out. This one is way more complicated. If it gets too complicated and you're not sure, you could use the same calculation that we did for chlorine when we talked about isotopes. And then you can actually calculate precisely what the mass number of this is, but you don't need to. And the reason why you don't need to is if you look at the elements, you can see that in two consecutive elements, there is actually a fairly big difference usually between the neighboring elements in mass number. It's rare that they're close. Like, look at this. This is one of the rare cases, but the two mass numbers are really close in size. But how about this and this? It's pretty big difference. So take a look. If I look at this, I can see that, first of all, what I can see is that this is not percentage. This is relative abundance. What does that mean? That means that 64 to 66, so these two elements, this one is double. So if this one is 30%, say this one is 15, because the peaks are double. So this one is present in double quantity, around double. Not exactly, see, this is a bit higher than double. So this one is present in double the quantity of this one. But let's take a look at this. So the highest percentage of this element has a mass around 64. However, you got these peaks at 66 and 68, which are pretty big. If you combine them, they're going to be bigger than this. So that means you also have this, which is not that much smaller. You got this, which is really small but has a high mass. So the average here should be actually around 66. Somewhere around 66. So let's just check. I mean, I would say it's a bit lower, but I didn't calculate correctly, so I just go to the periodic table and take a look. What is around 66? Okay, this is a great example of what I just said. So this element is zinc. How do I know? Because it can only be this one, or this one. It's not copper. Why? Because the average is 63.55. Here, we have nothing there. So it's for sure higher than this. It could be zinc 65.4, which is what I just said. So I would say it's slightly under 66. And it is probably zinc. Well, let's check the third option out. Gallium 69.7. So here, can the average be here? Of course not. So this is actually very, very simple in most cases. So this is zinc for sure. Let's say if we have that option. So actually this question didn't even ask which element it is. But this is zinc. Remember that. This is actually an excellent example of determining the elements. But this question is, if an element is found to produce the following mass spectrum, what can be concluded about the isotopes? Obviously, this element has 1, 2, 3, 4, 5 isotopes, right? So this is the correct answer. Remember this, I gave you some of these questions as practice, so you will need to be able to do this. This is in the AP. Oh yeah, let's take a look at this one. This one is kind of simpler. Why? Because the peak that appears in 138 shows that this isotope is for sure very high abundance. So this element is somewhere close to 138, but slightly under 38. So let's see if I got something like that in here. 138 is 131, 137.33. So could be this one, right? Because 137.33, that means it's like somewhere here. It's possible. I mean, this one is bigger, but there are 4 of these, and this is really low, right? So it could be barium. Let's see what's next. So you can see this is not next. Next is here. That's 138.9. Could it be here? Of course not. So obviously this is barium. So very, very simple to do this in most